going on, Algebra Bros? In this video, we're going to do an extra example of finding the zeros of the polynomial function f of x equals 4x to the fourth plus 15x squared minus 4. And you know what? I missed a word here. Find the real zeros, and we'll see why that's important in just a moment. So we'll start things out by setting the function equal to 0. And we'll start to construct our list for p over q. So the list for p is going to come from 4 or negative 4, whichever way you want to view it. Plus or minus 1, plus or minus 2, plus or minus 4. And then our list for q will come from the leading coefficient, which is also 4. So p over q, we'll start with fractions with a numerator of 1, plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 4. Then we'll move on to fractions with a numerator of 2, plus or minus 2 over 1, plus or minus 2 over 2, which, by the way, we already have that in the list with 1 over 1. So we can neglect that. It's no new information. And then plus or minus 2 over 4, which reduces to 1/2, which is also already in our list, so I'll cross it off. And then we'll move to fractions with a numerator of 4, so plus or minus 4 over 1, plus or minus 4 over 2, that's a duplicate. And then plus or minus 4 over 4, which is also a duplicate. All right. So now what we'll do is use the graphing calculator to graph the function. So in y1, we'll enter in 4x to the fourth plus 15x squared minus 4. And we'll get a sketch of that going. So 4x to the fourth plus 15x squared minus 4. And zoom 6. So it looks like this graph only crosses in 2 spots on the x-axis, and those would each be real zeros. We have a degree 4 polynomial, though, so you can have no more than 4 zeros. So a spoiler alert, the number of zeros a polynomial will have will equal the degree once we start considering duplicate zeros as well as non-real. So the fact that we have 2 real zeros might mean that we're going to get 2 non-real zeros. But keep in mind the problem only wants the real zeros, so it looks like we might have to only provide 2 answers here. We'll see once the time comes, but it looks like negative 1/2 and positive 1/2 are possibilities for these real zeros. And why I'm choosing those 2 fractions is because those 2 fractions come from our list, and if these 2 fractions don't work, then maybe plus or minus 1/4 will be the rational zeros. So here's just a little chunk of the graph. It's something like this, I believe. Yeah. And I'm going to guess with positive 1/2 first. And by that I mean I'm going to do synthetic division with 1/2. And here you got to be careful. Our polynomial function is missing some powers of x. So when we write down the coefficients, we want to make sure that we include zeros for whichever powers are missing. So for example, we are missing x cubed. So we'll have to put a 0 for that. We're also missing x, so we'll put a 0 for that. And then our last coefficient, or constant term, negative 4. Alright, so let's do the synthetic division. We've got 4. 1/2 of 4 is 2. Adding 0 and 2 gives us 2. 1/2 of 2 is 1. 15 and 1 gives us 16, and 1/2 of 16 is 8, and 1/2 of 8 is 4, and by golly, 1/2 is a real zero. That means we can start factoring the function f of x, and one of the factors would be x minus 1/2. Now the other factor will be built using this quotient polynomial, which has 4 coefficients, and the reason for that is because we started out with a degree 4 polynomial, and once we do this first round of synthetic division, that will force a degree 3 quotient polynomial. So that this is going to be 4x cubed plus 2x squared plus 16x plus 8. Now this quotient polynomial is not quadratic, which means that we should maybe consider another round of synthetic division to break it down even further. And here's where I'm going to use -1/2, or at least check this guess in synthetic division using that quotient polynomial's coefficients, 4, 2, 16, and 8. So let's do that. -1/2 of 4 is -2. Adding these down, we get 0. -1/2 times 0 is 0. 16 and 0 gives us 16, and then -1/2 of 16 is -8. And by golly, again, we get a remainder of 0. So 1/2 and -1/2 are our zeros, and we get to bust up that first quotient polynomial by writing the factor corresponding to -1/2, which is going to be x plus 1/2 due to a double negative. And then these will be the quotient of a quadratic quotient polynomial because we were dividing a quotient having degree 3. So that's going to be written as 4x squared plus 16. Now, we have at last a quotient polynomial that's quadratic. So our equation at this point is x minus 1/2 times x plus 1/2 times 4x squared plus 16 equals 0. And since that last factor is quadratic, we're going to set each factor equal to 0 to continue solving for x. Okay, solving the first two equations, we get another verification that 1/2 and -1/2 are real zeros. As for this last equation, I would consider using the square root method. And here's what I mean. We can bounce the 16 over to get 4x squared equals -16, then divide each side by 4, and we get x squared equals -4. Now, when we go to take the square root to get rid of that power of 2, we have to remember to include plus or minus. And we get plus or minus the square root of -4, which you'll notice there's a negative inside of the square root, and that's going to require us to rewrite this with the imaginary unit I. And the square root of 4 is 2, so it looks like the other two answers for x are going to be non-real. So in this section, since they only want the real zeros, we're only going to keep x equals 1/2 and x equals -1/2 as our answers. So let me make a list, real zeros, and that'll consist of the fractions 1/2 and -1/2. Now, if the instructions ask you for a factored form, we kind of have it with this equation that we constructed using the two zeros. But I'm going to do one more thing to it. Actually, a couple. First of all, we have a GCF in that third and final factor of 4. So I'll take the 4 out. This would be an acceptable factored form for me, but sometimes our author likes to write the factored form using just integers. And so there would be a way to get rid of the fractions of 1/2, and that would be by utilizing this 4. Now, 4 is the same as 2 times 2. And so what you could do is you could distribute one of the 2's to the first factor and the other 2 to the second factor. And in doing so, you clear the denominators, but you get coefficients in front of x. And long story short, here's what I mean. When you distribute the first 2 to the first factor, you're going to get 2x minus 1. And then to the second factor, you'll get 2x plus 1. And there are no more 2's to utilize, meaning that nothing's going to happen with x squared plus 4. So this would be the factored form version of the function when we only consider real zeros. Now in the next section, when we consider non-real zeros, we'll factor this even further. That is, we'll break up x squared plus 4 into factors which will include non-real zeros. And that is it for this video. As always, let me know if you have any questions. Otherwise, thanks for watching.